Good evening, everyone. This is Group 37, and my name is Osegonya Isaac, and my colleague Chanka Isaac Lusuku, and we're going to be taking you through multimodal EEG signal processing with body micro expression for driver cognitive risk perception using knowledge distillation. So to move on, I'm going to start with the background and the introduction. So worldwide studies consistently show that human error is the leading cause of car crashes or accidents, contributing up to 90% of those road accidents. So the goal was to build a machine learning model to help with reducing this number of road accidents due to the human error, which are the driver fatigue, just distraction and stress. So the traditional driver monitoring systems such as the camera-based drowsiness detection and the vehicle-based behavior analysis had limitations in accurately detecting cognitive impairedness. So this made us come up with a model driving monitoring system that integrates facial expression analysis with EEG signals and to improve the real-time detection of a driver impairment. So to move on to related works, we worked with the EEG, the technique that measures the brain electrical activity via electrons placed on the scalp. So we can talk about the EEG headsets. Then the advancement in the data fusion risk perception early warning system, because earlier on the traditional systems were focusing mainly on the external components of the car steering, eliminating the nerves, the emotions of the driver himself. So for us, that's what we are looking at. Then knowledge distillation involves transferring knowledge from a complex parent or teacher to a child or student model. Yeah, for more efficient model. Then in the context of multimodal EEG signal processing of a body micro expression, it has enhanced data for better accuracy. Then machine learning, high level computation enables machines to learn patterns and make predictions automatically. To move on to the problem statement, the domain application, the need of an AI-powered multimodal system that can predict the driver cognitive risk in real time. So here, as I told you, that first we want a multimodal to predict real-time real-time cognitive risk, such that it sends alerts to the driver telling him it predicts the state and tells him or her that warns them that in case don't do this, you're either drowsy or you are looking away from the car steering, or such that it warns him in advance, such that a road accident is prevented. So to move on to the computational problem, the need of huge computational resources, process massive EEG data sets. So here, you know how we need EEG data sets and image data sets, but you need bigger ones, which are really hard to work with. Then they require effective algorithm that can minimize time and resource usage without sacrificing accuracy. Then overfitting and underfitting. Then to move on to the research questions, we have what EEG patterns predict emotions such as fatigue, stress, drowsiness. Then how can machine learning algorithm be trained better to enhance EEG signals and facial expression recognition? What methods reduce overfitting and underfitting in EEG analysis and computer vision? So for computer vision, we basically maintain the vision transformer model. Then for EEG, we maintain the CNN model because they gave us the best results. Then the research objectives to develop an AI-powered the driver cognitive risk perception system to enhance driver monitoring beyond traditional system, to predict driving risks before physical symptoms appear, then to provide real-time warnings to drivers, to contribute to the future of intelligent driver assistance. Then to move on to our research contributions, we developed a model to aid in the prediction of the driver cognitive risk perception. We used the novel machine learning algorithm for improved development of our real-time cognitive. Yeah, I'll take you very fast through these. We developed a research template for the new studies on multimodal EEG signal processing, body macro expression for driver cognitive risk perception. As you see, I designed a scalable solution for detecting drivers' fatigue, concentration, and stress. Then we exposed areas in the context of our study that haven't been explored or existed. Um, yeah, so my colleague is going to be taking you through the dataset description and the EDA. So, my colleague.
Thank you very much,
Isaac, for that wonderful presentation. So, as my colleague talked about, we have been working with, we are going to be working with multimodeling. We are doing two data sets, and we're doing two data sets for two different kinds of data, and we have the we have the EEG dataset and we have the image dataset. So to start with, I'll talk about the EEG dataset. This is a dataset that is, first of all, we are going to be trying to first work with drowsiness detection. This is an indicator of fatigue in drivers, which is a very risky kind of scenario to find yourself in while driving. So the first dataset that we used was the EEG dataset that's able to capture and distinguish between a fatigued and an alert driver. And we worked with also an image dataset that is able to detect some certain kind of activities that could lead to risks of these drivers, put their lives at risk. For example, turning, turning like this, changing direction, texting, talking on phone, and other kind of potential behaviors that could lead to risks. It also has a safe driving kind of class to classify those drivers that are driving safely on the road. So moving on, I'm going to talk about the EDA that we did on our data set. So you can see this is just a brief demonstration of how our data is supposed to be described. And you can see we plotted an EEG signal over a specific period of time and show you how it works. These are different colors coding different kinds of signal channels on the head from different kinds of electrodes put to the brain. Then it has the division between the alert and the drowsy, or the alert and the fatigue class. And you can see that they are equal, they are 50-50, they are equally distributed. And then here we can see the different samples that we collected from each of the 12 individuals. And we can see that some individuals will have much higher than others. And this is a heat map to demonstrate our signals and their distribution. Then for the image data set, to start with at the right, I show you a demonstration of how different activities were recorded for our data set. And you can see that for the first one, this guy is safely driving, which is the first class. Then we have a guy talking on the phone, which is a risky kind of behavior. He had a guy who was texting, someone who was turning, and then someone who was doing some other activity that could put their lives at risk. Then we have a distribution of the different kinds of classes. That's a pie chart, also demonstrated with this bar graph here. We have some other kinds of plots that I won't get into due to the interest of time, but they are also there to demonstrate our data set and how it can be described diagrammatically. For more information on our EDA, I would refer you to older videos that we've been uploading on our channel. And we had a video that could explain the EDA better. So moving on, I'm going to talk about the system architecture and the methodologies that we used. Here is a pipeline showing our system and how it works, how our data flows through our system, and how our system is supposed to work. To start with, we start with the process of data collection, both the image collection and we also have the EEG collection of the signals, the EEG signals, through the electrode that is one on the head, and then the camera that is mounted in the dashboard of the vehicle. Then we have the pre-processing stage. They are where there's feature extraction, classification of different kinds of where we have the classifications. So after that, we have the classifications of these different classes, either fatigued or alerted, or either distracted, on phone, all those classes that we have looked into in their respective models. And then we fuse this data into a combined decision making model that is able to describe whether the driver is partaking into risky activity or they are safely driving on the road. And then this is later on deployed in an embedded kind of system that is in the vehicle. Moving on, we have models. We use the vision transformer which is the vision transformer for our image classification, and then for our image classification and then the EEG classification, we use the convolutional neural network because it performed better than all the other models that we used. So this is another kind of description of our methodology diagrammatically, and from the for the right we have the process for the EEG. This is now a separated into individual models, and on the right we have the image, how we were able to work around those. Then we have comparisons between the different models, and you can see that the CNN came out on top. These are EEG signals. We had a lot of models that we used. We also had ensemble learning, which demonstrates the multi-modeling part of our system. But we saw that it worked. It performed worse than the CNN. That's why we chose the CNN. And moving on for the image data set, the vision transformers, you can see, came out on top with better accuracy at a less training time than the CNN. So we chose that for our system. And then we have these two models. We have the vision transformer for the images, and we have the CNN for our EEG signals. So we did explainable AI, which we also described in a previous video. But to recap a little bit, we tried to do one for each of the best models and the worst models in each respective kind of data. And we had the attentional out salience map, so the vision transformer, which was the best, and then the wordcam for our images to better describe which of those areas our vision kind of models concentrated on when they were making their decisions in the prediction process. Then for the EEG data set, we use the permutation importance for our worst EEG model, which is linear regression, and then we use the sharply adaptive explanations for our CNN, which was the best model. So as you can see, those are the images that we concentrated on. This is for the vision transformer, and this is for the CNN, both the visual images, and you can see that they are concentrating on the human beings or the drivers, which is the main point of focus of our models to make their decisions. Then these are the explainable AI results, but by the interest of time, I won't go so much into it because we did a separate video on this that I recommend you go watch to better understand our explainable AI results. But this is the Sharply, which shows the most important kind of channels or the most important kind of signals that were very important to making the decision for this kind of models. This does the same thing but in a bar kind of manner, and this demonstrates it in this plotted kind of manner for both our best and then for our worst kind of models in the EEG signals. Then for the demonstration, we made a full video about demonstrating how our system works, but this is the user interface that we used to just kind of demonstrate how our model could be incorporated in the cloud. But our final deployment kind of method is in an embedded system that is able to track this in real time in the vehicles of the drivers. But this is just a demonstration user interface where we have a separate video talking about this. Then for the next steps or the future works, we have increasing the size and accuracy of our models and also implementing knowledge distillation, because we're looking at collecting more data. More data comes with more complex and more accurate models, but then to be able to feed them down into the embedded systems that are to be mounted in the cars, we're supposed to carry out knowledge distillation. We didn't carry it out right now because the models were relatively very small and they didn't call for knowledge distillation, but this is to be implemented in future works. Then multi-modeling data from different sources for multi-modeling image and EEG data, bringing them together to be able to make a final grand decision that is more accurate.
Then expanding the cognitive analysis by detecting other things like distress, distraction, and cognitive overload using EEG signals and prototyping and testing, of course. And also maybe incorporating an AI copilot that can talk in a natural language processing kind of manner using maybe LLMs that talks in a conversational way to the drivers and give them advice on which actions to partake in order to avoid certain risks depending on what our models are being able to detect. So conclusions. So our work is novel. We think it's revolutionary, and it can be very good importance to drivers all across the world, not just in Uganda. But with it comes a little bit of limitations, like the high computational costs, the accuracy of the subjects due to the variation in different EEG signals depending on the individuals,